Yeah, hello everyone, and special thanks to Katrin for inviting me and the very cordial reception here, but also the whole day, and to the people I was able to talk. And special welcome to Walter. Walter, I still remember we met the first time at the water detergents meeting in Aachen, long time ago. I think I was still a PhD student, and it was so fascinating what you presented on a detergent in the environment. And throughout the years, we have always been in contact. Thanks for taking time to be here this afternoon. Yeah, as already mentioned, I started with environmental water chemistry, and then I became interested not only in problems, but let's say in solutions, how they could look like. And that's the talk today. It's a lot of different topics, or maybe different topics. I'd like to show you that they are interlinked. And also, it's a pleasure to me to do this. And Katrin asked for this, to give this more general overview. Hopefully, it appeals to everyone, at least some of it, in the audience. I have learned it's an interdisciplinary audience, and therefore also this broader approach. However, it's not just about this. We have to put things into context. So the general outline could also be chemistry as a science, but also an industrial sector in context. Chemistry for whom? Chemistry for what? The same, maybe with a different angle, but also more or less with pharmacy. Yeah, if we talk about chemistry, normally you think about this. There's synthesis, then you get products, mostly molecules, nowadays also materials. Material scientists sometimes claim that they are not part of chemistry. From my understanding, they are, because they change materia. And then there could be some waste, and you need starting materials. That's it. And there has been a nice study published here from colleagues in Zurich, a huge success story. 350,000 chemicals on the market. Wow. That's a result of 150 to 100 years of industrial chemistry. Before, we had a figure of about 100,000 on the market in the European Union, so that this study was really a very enlightening one. So thanks for this one. Yeah, but normally you do not think about products of chemistry if you came across all this. And that's important also to have in mind. Yes, sometimes it's individual chemicals you are using, or the consumer is using. However, several chemicals, or most of the chemicals, are used by so-called downstream users, downstream industry. And these come up with the products you are using. But in fact, everything you see here and around you is chemistry. Now, that's often not seen, neither from the general public. You just use these products. You normally do not think of chemistry, that's fine. But later on, we will see, if you think about the material basis of life, of societies, and especially modern societies, you cannot circumvent chemistry in this broader sense of chemical industries and chemical sector. And I will not go into details, but nowadays we have the framework of green chemistry that came about because there had been a lot of environmental pollution in the 70s and the 80s stemming from production. Yeah, Love Canal, then there has been accidents like Schweizer Halle, Bhopal, Seveso. Yeah, and all these triggered thinking, and for example, in the US Environmental Protection Agency, but also in the European Union, there's also already a directive from 1996, which refers a little bit also to such principles. Also national societies like the German Chemical Society very early had a working group on sustainable chemistry. In fact, that came out from environmental chemistry. That's important to understand, because green chemistry as a concept came out from organic chemistry. Yeah, and that makes a difference how you see it. OECD was involved, many individuals. So Paul Anastas and John Warner did not invent this, but they did a great job to put this in a small booklet. Yeah, that was really, or becomes nowadays, to be a game changer. It's not yet the mainstream, even if we in the topic, the field, think it is. And there are several principles. One I will refer later on, design for degradation and design for environmental degradation. Katrin is also doing very nice work on this. I still remember the paper that came out of the peptides together with Martin, I think his name, Michael Zumstein. Yeah, very recommendable to read. So a closer look, however, shows that green chemistry focuses on synthesis. It focuses on processes and the products of synthesis of organic chemistry, the chemicals. Not all the products you have shown in the slide before. Or we can summarize, it's about individual chemicals trying to do this synthesis with less waste, less energy, also less resources, or specifically applies to renewable resources to come up with all the nice chemicals we are using, directly or indirectly. That's the one example of the backside of this huge success story. It's only 3, there are many more. Yeah, I have no slide about chemicals in the environment and the nice paper that recently was published, pollution in terms of planetary boundaries. Yeah. But here, I guess most of you know these examples. Textile waste, maybe you were not aware that there are normally several hundred chemicals involved until you get your nice textile. Yeah, there are several thousand on the market. Not all are part of the product, but some are used, for example, for better processing of the fibers, etc. 600 is already quite a bit, so because each chemical is an individual, right? Like we are here. We are all chemicals, humans, but each person with a different character, different reactions in different situations, yeah, and so the same with chemicals. So that's only a minor part of these 340,000, but it's still quite a lot if you should handle them, analyzing. Nowadays that could be feasible, at our time not yet, but still risk assessment you need for them. Maybe you need something about how they behave in effluent treatment. Often they are not treated, they are still stay on the product, the textile. And then these textiles, also outdated ones, we are using are not all just recycled as for fibers, as for dyes, because sometimes it's not feasible, sometimes it's too expensive. Often they are then back to the countries where they are produced. So we have a first sustainability aspect here. Chemistry in a context. We should not export all our waste and the dangerous chemicals on there into these countries where they are landfilled without special equipment on the basis that chemicals do not go into the groundwater. Yeah, then I think that's well known nowadays. The microplastic, the media like, but probably the bigger issue is the microplastics, and also it's a highly complex mixture. It's not only the polymers, I will show you later on a slide. It's also additives to modify properties. And yes, it's a nice idea to skim all the plastics on the oceans. But sorry, guys, 2/3 are already on the seafloor. So that's a long-term impact of what we are doing. Yeah, and that addresses already a little bit some of the shortages of green chemistry. First of all, chemistry itself is non-normative science. Molecules, atoms do what they do according to their nature. If we set specific conditions, especially in industrial context, to get something specific, then it's our wanting, our human value proposition. That's important to understand. That makes a difference. The same holds also for green chemistry, and I call it greener. Why? Nature does not tell us what is green or what is good. We can only assess by comparison. There's a route of synthesis, type of waste, properties of a chemical, less hazardous, etc. Yeah, and if you do risk assessment, what is more dangerous? Mutagenicity or endocrine disruption? How to weigh? Yeah. Then not addressed by green or greener chemistry, it's focused on the individual product or molecule, not the flows that are resulting So if you're successful with a new molecule and it's used in 1,000 or 10,000 scale, a tonnage of scale globally, yeah, at different places maybe, but in the end it sums up. Yeah, and that's not part or not involved into green chemistry. That's quite understandable. Yeah, that's not my point. The point is that we have to be aware of this. And sometimes the sheer amount is a challenge of chemicals, even though they are not really toxic. But too many chemicals on one place at the same time could be a challenge already. Yeah, so that's this part. Also, it's not addressing the mixing of chemicals for products. Also in substance and material flows, it's always like most risk assessment of chemicals, it's individual chemicals, it's individual products. Recycling is not included and ethics is neither included. If you use, for example, cobalt as a catalyst in a nice synthesis, catalyst saves energy. But often cobalt comes from Congo, where it's mined by child labor financing civil war. Should chemists stay away from this knowledge? At least I think you should know about as a chemist. I mentioned waste, and on the other hand, I think that's always also clear now. Resources are running short. Yeah, so the fossil age is just the peak along the time. Very helpful without the fossil age also to make clear before criticizing. Without the fossil age, we wouldn't have our standard of living, our technology, etc. It starts already if you want to transport all the goods and the raw materials, you would need more than the surface of the earth to feed all the horses. Yeah. So yes, I will criticize some things, but on the other hand, without this, we have to be aware we would not be there. Water, I think that's a place here where I do not need to spend any more pollution of water, yeah, which in other fields and hydrologists often think in quantity, but now more and more we see also the issue of quality worldwide. So if there's a flooding also in our country, then we see more and more it comes also along with pollution, but also we have everyday pollution. What's not removed in our countries by a sewage treatment plant, for example. Yeah. And then renewable resources, I mentioned already, they are also limited. Many people nowadays think, oh, let's go for renewable resources. Let's grow all the organic stuff. Great. That will not work. And I like the other one, copper mine Casa Grande in Arizona, because it shows we have to dig deeper. Literally, we have to dig deeper for the metals, yeah, to get out the stuff we want to have, copper especially for the new electricity society. Yeah, we need copper for several reasons. And the low grade, the low hanging fruits are more or less already harvested. And a lot of environmental pollution comes along with mining and a huge energy demand. Yeah. Just a few keywords here I want to mention. And also we have learned availability and accessibility is an issue because not all resources are available or from at each place on this planet. Just think of metals, for example. Yeah. Good, so I think it's quite clear, and that's one of the drivers to bring together waste and resources, and that's the starting point. I think that's clear for circular economy. What should be the role of circular economy, which is also a normative framework? What should be the role of chemistry within circular economy? The good thing is materials and products come into focus, not just the chemicals, but what we make of them. Yeah? And that's, again, a good step forward. But what you can also see, not everything that's synthesized according to the principles of green chemistry does necessarily fit into a circular economy. Therefore, it's important to understand these differences, to be able to act as, how should I say, good or targeted as possible. Therefore, that's important. What we see now, a few challenges of the circular economy. We see, for example, increasing chemodiversity. Biodiversity is endangered. Chemodiversity, we have the opposite. It's growing, it's increasing. It starts with the elements we are using, for different purposes. More or less the whole periodic table nowadays. And to be honest, when I studied on a voluntary basis, I heard a lecture from a nice, very good professor, but it was just out of curiosity about rare earth. Never thought that I could use this. Now, doing research also on metals and their usage and dissipation, I'm glad that I have been in contact. So that's a message to the younger in the audience. Maybe sometimes do not always think about, is it valuable? What can I do with it? Just be curious. You never know what happens. That's a side aspect. Yeah, so, and we can also see the chemical abstract service, numbers of compounds registered there, how it increased. So in 2060, in this year, probably 2090, you see how much was registered there, much more than has been registered here within a decade. We have now within a year. Not all of these chemicals make it to the market, but if you assume maybe it's every 10,000th, then you will see also what we have learned, 340,000 chemicals. Probably that's not yet the end. And it's not just a number, it's a huge diversity. That's the challenge here. To deal with diversity needs energy, needs knowledge, etc., etc. Let's have a look on products. Soccer shirt of the Swiss goalie in football, shirt. Normally we think, okay, it's a nice shirt. What you have here, it's polyester. That's one of the basic fibers. Then you have cotton. So it's a mixed fibers shirt. You have elastan, also a polymer. Then polyurethane for the applications especially, also a polymer, but a different one again. Then you have dyes. And as I mentioned already, again, all the other chemicals. So think about how you would recycle this mixture of fibers and other stuff. And sometimes you have applications on textiles for glimmering and reflecting light or so on. That's even worse. So these are the products. We talked about polymers. It starts already at the chain, at the basic building blocks of the polymers, where we have a diversity. Okay, in polyethylene, we have the same building block. It's also ethylene, ethylene, ethylene. Yeah, that's fine. But already there, we have mixtures of atoms and functional groups, but that's not all of it. And there are no exact data, but estimates say we have about 100 different polymers on the market. Maybe the people could do all of this research. And then you can see also in a nice study, more than 10,000 additives. So other chemicals are added to modify properties of polymers. Flame retardants, antistatics, whiteners, colors, for example, you can use, or PVC, maybe you know, and you have experienced that's a soft material, for example, from the mantling of electrical wiring. Pure PVC is a very hard stuff at room temperature, very rigid. So additives are added. Environmental chemists know about the phthalates, phthalate ester. Release from polymers is one reason why we found them in the environment. Or maybe you have a nice pencil, soft and so on. Wow, good. Then you store it away for 5 years in the drawer of your desk, and then you put it out and say, it's a bit greasy. And that's because these compounds migrated to the surface. And they are also going to the indoor air and the environment. Flame retardants the same. Here we have a sketch of a foliage for wrapping food, packaging of food. 7 layers of polymers and additives. Additives are also polymers, in fact. And not recently, 3 years ago, I was on the holidays on one of the North Sea islands. I walked into the supermarket. On the left side was a traditional food. On the right side was organic food. And the organic food was wrapped with plastics, endless. And I asked them, why do you do this? Yeah, we have to protect against pollutants. And we have to keep it fresh. It has to look fresh. Okay, if you want to store it for several days, then you have to. But is that what we need? So we think it's fresh, but it's not fresh. Yeah, so these are some of the examples of complexity of products. The next ones maybe you have heard about. If you have a look into a mobile phone, we have metals in there, 40 elements, and also species, as chemists call it, different oxidation states. Only the blue ones are normally regained during recycling because of value, because of amount in there, etc. Many of the others are lost, a so-called waste. And we have also polymers, plastics, silicones, etc. Highly complex product. To be honest, my aim is when I'm retiring that I do not need any more smartphone. Maybe just an old mobile, okay, but just using it as a phone. Because then probably I will not travel so much, no need to have the Deutsche Bahn app or Swiss Railway on it. Yeah. Okay, we will see whether I will manage. Think of your car. A car is a huge collection of polymers, including additives. Or you can also say it's a computer on 4 wheels. So we have all the stuff we have with the mobile phone. Highly complex products. So we thought about what could this mean for recycling. It's clear for recycling it's a challenge. If it's possible at all to separate all these components, then you need lots of energy, lots of reaction steps, lots of treatment steps. Starts with separation on a microscopic level, and also then down to the atoms. And if you use compounds that are very similar, think of rare earth metals, they're all very similar. Sometimes it's more or less impossible to separate, or you need huge energy impact. So for that chemistry or the products of chemical industries fit and material science included fit into a circular economy, we really need to reduce complexity on the atomic level, on the molecular level, and the material level, and probably also on the product level. Do we really need 30, 40 different mobile phones? Different compositions? Or maybe 10 would be enough? I know we are now talking about ascesia, we are talking now about freedom. I have made the experience to have less. Some examples gives you more freedom. And to have a clear fence of freedom, or the other way around, I find it challenging to think about which of these 40 mobile phones should I take? And I also experienced times when I sat in front of my computer finding out what are the difference, what could be the best. What a waste of time. What a waste of time and resources later on. So we should avoid complex products if possible. So we should keep the atomic and molecular complexity and mixing at the minimum, because each separation in recycling needs energy. There could be physical separation later on, metallurgy, for example, and results in waste. There's no physical chemical process without waste. Even if you recycle something, there is waste of the recycling. It's good to go for recycling as much as possible. Sure, because if you think of metals, if you do recycling, saves you a lot of waste and energy compared to extraction, to mining. But the question is about the level. We should minimize the use of components that cannot easily be separated, recycled. That's the summary on this respect. And also minimize mixing. Yeah? And for the chemists, mixing always means increasing entropy. So think of thermodynamics, material entropy. And that's the background of loss and of waste and energy in addition needed for separation, unavoidably. And we should avoid from the very beginning, so the design aspect also, not suitable materials, not suitable for capture and recycling at the end of life. Maybe even more, maybe products that we cannot collect. Think of the tiny earplugs you are using nowadays. How many do you have at home? Do you know where they are? Will they ever be ever collected? When I was young, we had also these earplugs, but it was only one and only for a short time because it was so noisy, so terrible, because only copper was in there and not the high performance magnets we have nowadays needing, or for example, neodymium, a rare earth metal. So that's just one example. You just think about, look around in your personal life and you will see more. And the same holds for processes. And on a level above this, we should also think about sustainability. That means we should think beyond molecules, materials, and products from the very beginning. So you see the design is from the very beginning. And that is one of the lines of my lecture, and Benign by Design, also what Katrin is doing. There is, I hope it's true, a quote of Albert Einstein. He said, a smart person solves a problem. A wise person avoids it. And we are also well educated and trained in solving problems. What about avoiding? Maybe you need even more knowledge, not less. Yeah, so there are sometimes rebound effects and trade-offs. For example, modern societies, we want to get rid of carbon dioxide. Yes, low carbon, but that often means high metal. So we have to think about, that would be a rebound effect, we have to think about energy efficiency and what we really need. Not what we want, but what we need. That's the difference. And the other thing I mentioned already, reduce and simplify diversity of dynamics of substance, material, and product flows. Also size them down in terms of space and time. That means not circulating everything globally. If you look up how many transportation and different locations are needed nowadays to build a car or to build a mobile phone, several times traveling around the world. Maybe you should produce more for the local market at the local place. What we still need, we have to make sure that we know where things are, else we cannot get hold on them and will not be able to recycle them. That's traceability. And still not at the end, we need appropriate matrix. Sometimes this could be a highly complex LCA, but that's not always necessary because sometimes it's already clear. You see on some of the points I have written down here. There's not a LCA, the basis of it. It's just, how should I say, sound thinking, system thinking, broader view, beyond chemistry, if you are a chemist, for example. Yeah, and we have to change traditional chemical practices based on bigger, faster, more complex into optimal, adapted, better, safer, and less complex. I find this not only a challenge, but I find it really inspiring and a huge opportunity for the next generation of chemists. And we see that the young chemists are very interested in such topics. So I'm very optimistic that we can be able to make this. If you have to go for recycling, and that's what people normally think if you talk about circular economy, recycling very often pops up. No, first, we should think about reuse, use as long as possible. That means circulate, yeah, and then maybe use for different purpose. The same polymer maybe is of lower quality when it's recycled, or just remold something. Yeah. So first we should cut form and size, and not cutting down things, fibers, alloys, metal pieces, and so on. If that's not possible, we should keep material, at least, if we go for recycling. Then it's, again, about recast, metaling, metals, alloys, glass, thermoplastics. And first design rule already, avoid thermothets. Why? Because thermothets you cannot remold or recast. If you increase temperature, thermoplastics get softer and softer in the end, like a liquid or a high viscosity thing, and you can give them a new shape. With thermosets, you can't do. Above a certain temperature, they just start to be oxidized, to be destroyed, and you end up with carbon or some similar stuff. So avoid thermosets, for example. If that's not possible, then keep at least the basic building blocks of molecules. So what chemists often see as a first point to act, depolymerization of polymers, is only on the fourth one. So chemistry and chemists, maybe we had a huge success story, but we have to learn that we need to be a little bit more humble in the future. And we see a lot of discussions going on. Oh, this plastic, it's all mixed, so let's go for pyrolysis. What do you get out of pyrolysis? Again, known since more than 30 years. It's a high temperature, non-targeted thing. You get out a lot of molecules. Also, a lot of molecules we don't want. Even if there are some you want to know, you want to have, you have to separate. And what's often called thermal recycling, sorry, for me that's a fake. There is no thermal recycling. It's just combustion or incineration. You lose the material and some of the energy in there. All the energy that has been invested to make it. So the new thinking is the design. And then we have the full picture of chemistry in a circular economy. The design, and first think about circulation, then you need to think about durability, for example. You need think about use. That's a good starting point very often. If you go for benign by design on the circular economy level, that's also benign by design. Disassembling is important. Self-repair, so the polymer chemists can contribute here, for example. And make sure for the recycling that this is as little as possible, as low as possible. And you can use it as a resource. But the most important thing, start first thinking before you act. And also, maybe to many not new, but for some maybe, there is no endless recycling, or sometimes you hear upcycling. Upcycling is a possibility in terms of economics, so you can increase the value of a material. But that always comes along if you're grading up, for example, copper, you create also a lot, you generate slag. And slag is waste. You cannot get out the copper anymore there and other elements. So be honest, there is no upcycling. Maybe there's a further use of something, but often that's only one cycle only. If you use a tarpaulin of a lorry and you make bags out of it, yes, that's fine, but you're cutting a big sheet of things into pieces. And students like this, or people, in the worst case, they throw away or do not use the bag they have bought a year before. And then they use it a little bit. And because it's already a used material, maybe lifetime is not so, and then it's also thrown away. It's still the old thinking. Yeah, the points I have already mentioned, and there are pollutants. Think of the additives in the polymers. They cannot be recycled. Often they are then pollutants, flame retardants, highly toxic, persistent. If you want to have a good material out of the recycling process, we have to depollute all the material flows. And not all chemicals and products can be circulated. It's often also overseen. But first, thermodynamics for the chemists, physical chemists, different words, as you probably have learned. First law, you cannot win, you can only up in a draw. Second law, we can only up in a draw under perfect conditions. Sorry, guys, there is no perfect conditions. If there would be perfect conditions and no thermodynamics at work, I would not get older, for example. Yeah, so what we cannot is win, but what we can do and should do, try to lose as little as possible. And this has to do with what I have told you before, and also I called it here decrease, or some call it degrow, but I have here applied it to chemistry and products. I think that's a sort of a summary I have already mentioned. Coming back to not everything can be circulated. Mentioned already, polluted products could be by use, but also, as I mentioned, because the composition originally there. Then we have toxicants also that have been formed during use, oxidation or something like this. And also products that enter the environment by intended use or as a follow-up as intended use. Pesticides, pharmaceuticals, laundry detergents, Walter, right? Sooner or later, and so on. Personal care products. Then we have unintended losses, abrasion from surfaces, weathering of a facade of a building, for example, abrasion of tires, yeah, and I mentioned already reaction products of transformation within the life cycle. These we cannot get hold on, cannot recycle. And just a brief sketch, what we are talking about, numbers tell us it's about 30,000 chemicals, according to German UBA, that are environmentally relevant. I'm not talking about the products of incomplete degradation, of incomplete mineralization, the so-called transformation products. They are not included here. Including them, probably I would expect we are talking about 100,000. Most of them we do not even know. We do not even know whether we can analyze all of them, let alone the quantification or ecotoxicity testing. The goal is, in this case, to have clean water. Yeah, still. So let's go for sewage treatment. Just summarizing. I know maybe that's a hot topic here and I shouldn't mention this here, but I'm not so in favor in general of advanced effluent treatment. Needs a lot of energy. You have to deal with additional chemicals. We do not always know how many transformation products are formed, how toxic they are. Sometimes they are nicely removed, in good cases even mineralized. Yeah? But we should stay away from the thinking everything is mineralized. Yeah? See the transformation products, for example. Then sometimes the water is not treated. Combined sewer overflow. Water is circumventing the sewage treatment plant that it's not damaged. We have increasingly broken pipings in the underground. Yeah? And if we go for sustainability, we have to think also globally. 80% of world's effluents are not treated, according to UNEP Water, and probably never will be. So we need not only sewage treatment plant or sewage treatment plant upgrades. Sewage treatment plants is fine. Really needed, has been one of the big progresses in mankind and health, owing to the engineers, not to the medical doctors. Yeah. So no doubt about that, but obviously we are approaching a limit here. Or do we want to add a 5th, 6th, 7th, 8th stage for treatment to really remove maybe at least all the chemicals? Yeah, so what can we do in this case at the beginning of the pipe? Again, it's about avoiding things. That means go back to the beginning of the pipe. I know I have to speed up. Okay, so, and that's the benign by design for the environment. So in short, is, as already mentioned, now on a molecular level again, start thinking end of life. Where will your product end? If it goes to the environment, design it for complete and fully and fast environmental mineralization. If it's circulated business to business, maybe it's better to make it as stable as possible. Solvents, for example, if you can make sure that nothing is going out into the environment, or only really tiny amounts. That's the core of benign by design, also for rendering molecules environmentally biodegradable. Meeting on the one hand the functionality that is needed, very challenging with pharmaceuticals, yeah, and on the other hand, degradation in the environment. We can take advantage that in the environment we often have different conditions than in the realm of application of the chemicals. For example, diversity of metabolic enzymes or diversity of bacteria that are around in our gut and in the environment, sewage treatment plant or in the soil, pH, redox potential, excess of light, temperature is often different. We are just at the beginning of this. I think there's a lot of opportunities we have, but we have to better understand how to take advantage of these different conditions. Yeah? Therefore, if I talk about biodegradability, I talk about environmental biodegradability, especially in pharmaceuticals. That does not mean biodegradability in the human body, then we have a first pass effect, would be not a pharmaceutical. We worked a little bit on how this could be done. I will not go into details, but you can start with a new lead structure for pharmaceutical, but also for the other application. So that we call de novo. And but you can also redesign de novo. You have the advantage. You can really come up with something new, but you need another more additional knowledge on a receptor or properties where you want to apply, etc. With a redesign, you have all this knowledge. However, it might be more challenging to find the patent gap. Yeah, and you can do this in a non-targeted way. For example, if you do a photolysis of a compound in water, you get a lot of follow-up product. So maybe there is one that has the properties you want to have, and at the same time, it's environmentally biodegradable. Chemists say that's horrible because it's not a synthesis. I call it non-targeted synthesis, because synthesis is about making new chemicals. Yes, this you can do, or you can do this on a targeted way, this redesign, and here the in silico tools come into play, for example, and you can start with in silico, you can start with experimental. All this is possible, depends of the molecule, its application, and so on. Yeah, and the same also for de novo. If there's a new lead structure, you will try to optimize. Yeah, you can do this. And there's also a workflow we have published. Maybe, surely it can be improved, but it's a starting point. These are some of the examples we did. And I mentioned already the peptides Katrin was working on. It's pharmaceuticals. Even there, where the things you had to meet are most challenging in terms of unwanted toxicity, biological activity, even there it's possible. And here, that's my favorite one, ciprofloxacin. Maybe, Walter, you remember. You have your cyclopropyl ring. We were able to come up with this new compound, comparable properties. And we could even patent. Why? Because we did not think on stability. We thought, as chemists do, in kinetics and half-lives. So hemiaminal, that's this structure for the chemists, can be cleaved by acids. So this compound falls apart in the bladder after excretion, but it's stable enough for several days in the human bloodstream. And the parts that are formed are easily biodegradable. Also ionic liquids, we could show using green starting materials or renewable. Yeah. So just coming slowly to an end. And that's already sustainable chemistry. I mentioned this in the beginning. We have to think about service and function. And if we do this, then we come across often with other things. First, different behavior, different construction, or education. And I will present you a few examples. We are working on silicones, rendering them environmentally biodegradable. When I first talked to the companies using silicones in cosmetics, never, never, never we can abandon these compounds. And then I asked why. Often they said, I don't know, but we do it for decades. Then I recommended go back in the archives of your company, try to understand why, and compare whether this applies today. Nowadays, they are advertising everywhere, without. Wow. In some cases, maybe there's another chemical in there, we still have to learn, but not always. Yeah. And companies learn, wow, we can sell this even more expensive with less material we have to buy. What a return of investment. What a business model. Wow. More money for less you get, or you have to pay. There has been nice work by a colleague, Michael Burkhardt, here in Fachhochschule Nordschweiz about things from Facades. We also did some of this, and we have been told biocides in Facades, indispensable. Then I came across in a market without biocides, as you can expect. Sorry, a little bit more expensive. But it works, obviously, with less. And again, function. Don't forget the old stuff. I'm a huge fan of Bauhaus architecture. but I'm afraid I have to get rid of it. If you can go to all cultures over the centuries, they knew already to protect your facade against water and to use the right material. So the modern stuff is not always the better. And that's also a nice example of construction instead of chemistry. Maybe you know this. At least I have discovered in Denmark, but I remember 20 years ago, this one was the standard, not this one. I had no idea when the other one came. So at least you save, again, material if you produce it, and you can easily separate and recycle. Less is more. Pharmaceuticals. These are data from the European Union, OECD, Netherlands. These are standardized data, so-called defined daily doses per capita. And you see Greece threefold the Netherlands. And I do not assume that the bacteria there down are more aggressive or more or whatsoever. Obviously, culture plays a role. Education of medical doctors. By the way, if we would go for meat production, Netherlands would be the worst and Norway the best. So it's not blaming a certain nation. And this goes through there, I think about 20 pharmaceuticals they listed like this. And it's always different, the position of individual countries. In a hospital, it's not about maintaining, using as much disinfectant to maintain a certain hygiene standard. It's to maintain the hygiene standard. And with this view, you start thinking about, where do I really need to disinfect? And you have better focus on education. And the edges are then round, because then you can then you can clean them more easy. And there is no disinfection may be needed. And by the way, bacteria do not just jump from the floor on the operation desk. Think about the anxieties you have. Okay, so that's the big picture. They're quite complicated, but it also gives a lot of opportunities. Sustainable chemistry. And one thing to also, it's all about design, and design includes also service and function. At all levels, and that's the final one. I mentioned in between system thinking, non-chemical design, alternative business models, the disinfectants, but also the nowadays examples from car industry, not paid kilogram or ton of solvents you are delivering, you are paid by square meters you have cleaned. And if you do this, then you think about how can you do the same job with less? And there's a totally different communication between if I'm the deliverer and my customer. Then we think about to share experiences and how can we improve? So it's a common interest. In the traditional model, tonnage, the talk is about, I try to sell you as much as I can on the other sense, and I will try to pay as little as I can. And that's it, full stop. We have to improve the communication along the whole life cycle. But sustainable chemistry is also a human value proposition. But again, that's an opportunity because we can change our value propositions.